So hi, thank you for having me. Everything works, audio, video works? Okay, perfect. So hi, thank you very much for inviting me to speak. It's my pleasure to show my work to a broader community. It's also a nice way to finish my summer vacation right before school year starts. So this is going to be an overview of work I've been doing with different people for the last 5 years or so, but I'll try to focus on the more recent results. And every theorem here is joined with somebody else, and I'll say who proved what. All right, so I'm a graph theorist. I work on graphs. Let me see if I can move this. Just 1 second. All right, so when you think about graphs, some graphs are complicated and some graphs are simple. And there's nothing we can do about it, but it's nice to at least be able to distinguish between them and say, this graph, we have high expectations from it. It's an uncomplicated graph. We can hope to do things to it algorithmically or understand its structure. This graph is a complicated graph. There's no hope. You have to do something else. And there are different ways to measure the complexity of a graph, but one of them that's been productive is by looking at something called the tree decomposition of a graph and trying to see if this tree decomposition is simple or complicated, and based on that, classify the graphs. So let me tell you what the tree decomposition is. Now, if you've never seen tree decomposition, this is probably not the time to learn, because it's a concept that takes some time to get used to. So you can just think of it as a way to represent a graph using a tree. I give you my favorite graph and I try to construct a representation of it via a tree, and then I'll measure how efficient my representation is. So I'm going to tell you the definition anyway, but you can choose whether you want to think about the definition or if you want to think about this more high level picture of take a complicated graph and represent it by a tree. Okay, so here is the actual definition. I start with the graph G and I define a tree decomposition T chi of it, where T is a tree. And then what I do, I assign to every vertex of the tree a subset of the vertices of my graph G. And in this definition, I'll say node for the nodes of the tree and vertex for the vertices of the graph, just to make it a little easier to listen to. So to every node of T, we assign a subset of vertices of G, and we call this the bag at V. And there are several rules, right, in order for it to be a representation. So the first rule is every vertex of the graph needs to appear on some node of the tree, right? You have to put every vertex in some bag. The second rule is for every edge of the graph, it needs to appear in some bag. So for every edge of G, there's a node of T, so that both ends of this edge are in this bag. And then the third rule is kind of a consistency rule, right? So far I just said, you have to put a lot of things in bags, or you have to put certain things in bags. And now the last rule is sort of what ties all of it together. So the last rule says, if I look at the vertex of G, and I look at the bags in which it appears, and I put it in this bag and I put it in that bag, and then I look at the path between these two bags in the tree, I have to put this vertex in every bag along this path, right? So let me write what I wrote, but it's the same thing. For every vertex of G, if I look at the support of this vertex, namely the nodes of T in whose bags it appears, then that has to be a subtree of T, right? If I have the support of the vertex of G has to be connected. Okay, so let me do a couple of examples. So the first and simplest tree decomposition is you take your favorite graph and you take a one vertex tree and you put all the vertices of your graph in this one bag. So that's a tree decomposition. Every vertex is in a bag, every edge is in a bag. There's kind of no consistency to check because there's only one node in the tree. But we can all agree that this is probably not a great tree decomposition. I didn't do anything. My bag is as complicated as the graph I started with. That's not a way to represent things. Okay, but let's keep that decomposition in mind. So now let's do another one. So in this picture, this is the graph, and this is a tree. You can see that they're the same, but they're different color. And so I have my graph, and I numbered its vertices. And now for every node of the tree, I just need to tell you what the bag is. And so here's a rule. I designate a root for my tree. And now for every vertex, there's a unique path to the root, except for the root itself. That one's already there. So for every vertex, there's a unique path to the root, and it has a unique neighbor and its unique path to the root. And what I'm going to put in the bag is the vertex and its unique neighbor and its unique path to the root. So for example, 1, its unique path to the root is 1, 2, 3. 1's unique neighbor and its unique path to the root is 2. So I'm going to put in the bag that corresponds to 1, 1, and 2. 4, its unique path to the root is 4, 3. Its unique neighbor and its unique path to the root is 3. So what I'm going to put in the bag corresponding to 4 is 3 and 4. And I've done it for every node. You can check. I'm not going to check that it's 3D composition, but it's not hard. So this is a little bit better, except at least the bags are not as complicated as the graph I started with. This is still a dubious way to simplify something, right? Here I had a tree and a number on every vertex, and here I have the same tree and 2 numbers on every vertex. So that's not ideal yet, but let's keep going. So here is another graph. This is a cycle. And now I've constructed 3D composition of it. Now the way I constructed this 3D composition, I first removed the vertex 2, and I noticed that what's left is a tree. And then I constructed a 3D composition of that tree using the rule that we made before. And now I checked where 1 needs to go. So the edge 1, 2 needs to be somewhere. So I put 1 in this bag. The edge 1, 6 needs to be somewhere. So I put 1 in this bag. And then I remembered the last rule that if 1 is here and 1 is here, then 1 has to be in every bag along the way. So I did 1 to this and I did 1 to that. Okay, so that's a little bit better because there's definite simplification here. I started with a graph with a cycle, and I represented it by a graph without a cycle, which was my goal. And here I started with a cycle of length 6. I could have done the same thing to a cycle of length 100 or any length, and the bags would still be of size 3. So that's we achieved something. Okay, so we had 3 examples. One was there's only one bag and it has size n, the number of vertices. Another one was 3D composition of a tree and bags have size 2. Another one was this slightly more general example and bags has size 3. So let's now try to make this more quantitative, right? What's the difference between the first decomposition that I said is no good and this last decomposition that I said is getting somewhere? So I want to measure how simple the bags are. And there are many ways to measure it, as it turns out, but let's start with the first thing people thought about, and that's the width of the 3D composition, and that's the maximum size of the bag, except you say -1. The reason you say -1 is because you want for this decomposition of a tree to have width 1 somehow. This is the simplest thing you can do, so you want this to have width 1. Okay, so the width of a decomposition is the size of the biggest bag -1, and then the tree width of a graph is the minimum width of a decomposition. So it's a min-max, right? In every decomposition, you look at the worst bag in it, and then you minimize that, and that's the width of the graph. Okay, so that's tree width. It's something that's been around for 40 or 50 years. And we say that G has small tree widths if and only if it's close to being a tree. So we designed it so that the tree width of a tree is 1. So trees have small tree decomposition. What about in that direction? What is this close to being a tree mean? And trees have many properties, but the property I want to focus on, in which having small tree which is the sense in which having a small tree having small tree widths makes you close to being a tree, is the following. In a tree, you have the property you can remove a vertex and your tree breaks into 2 roughly equal parts. So that's the property I want to focus on. Roughly equal means each half is at most half the graph, or at most 2/3 of the graph. So that's what I want to focus on. If a graph has small treewidths, I can remove a small set of vertices and then again break it into parts of roughly equal size. It's not easy. It's not hard to see that if you have small treewidths, then you can do it. You can find this what's called a small balance separator, and it's a hard theorem that if you can do it for all weight functions, then treewidth is bound. But this is what we're going to say. Now, this is a good thing because of the way algorithms work. If you have a small balance separator and you're trying to solve all kinds of algorithmic problems, what you can do is guess the solution on the separator and then try to extend it in this direction and that direction, and you can do that in polynomial time. For that, you need that the separator is small and the parts are each part is at least 1% of the graph. Like which problems can you do that for? One kind of benchmark problem I want to think about is the max weight stable set. What's max weight stable set? So first of all, a stable set in a graph is a set of vertices with no edge inside. And secondly, so what's max weight stable set? You're given a graph with weights on the vertices, and you want to find a stable set with maximum weight. Okay, so that's a well-known NP-complete problem, but on classes of bounded treewidths, you can solve it in polynomial time. You can do what I just said, keep picking small separators, or you can use something called dynamic programming, which looks at the whole tree decomposition at once, and the complexity is a little better. But let me not explain how that works. So the point up to here was to define treewidth and then to say small treewidth is good for you. For example, you can solve NP-complete problems on graphs of small treewidth. So we said bounded treewidth is a good thing because of dynamic programming, but actually, that was, like I said, that's something that's been around for a long time. But recently, people started thinking about other algorithmically useful properties of tree decompositions. So, for example, if bags don't have bounded size, but they have size that grows slowly with the size of the graph. So if bags have size logarithmic in the number of vertices of the graph, you can still solve max weight stable set in polynomial time. If all bags have polylogarithmic size, right, so log the number of vertices to some power, well, you don't get polynomial complexity, but you get what's called quasi-polynomial complexity. So polynomial means n to the number of vertices. Quasi-polynomial means this, the number of vertices to some power of the log. So it's not quite polynomial, but it's very far from being exponential. So now another possibility is, what if your bags have small stability numbers? So their size is unbounded, but the size of the biggest stable set in them is only bounded. Well, it turns out you can still solve max weight independent set in polynomial time, and the reason is really to do either dynamic programming or this guessing of the solution on a small separator. All you need to do is be able to look at all subsets in the bag or in the separator in polynomial time, and for that, all stable subsets of the bag in polynomial time. And then you can do if the number of vertices, if the size of the biggest stable set is bounded. And then the last thing that's useful is when all bags have a stability number which is polylogarithmic in the size of the graph. And then again, you can solve max weight stable set not in polynomial time, but in quasi-polynomial. So we said there are other things that are other bounds on treewidths that are useful algorithmically. Structurally, that's something that happens in well-structured classes of graphs. It's in most graphs, you're not going to have any of these properties. So it's an interesting property of a graph class. Does one of the things happen or not? So I want to focus on this last two things that I said. When instead of looking at the size of a bag, we look at the stability number. And that turns out to be an especially nice property to work with, so nice that it has a name. So the tree independence number of graph is something that was defined by this group, Dallard, Milanich, and Stogel. So that's exactly what they said. They said, let's define alpha of a 3D composition, the stability number of a 3D composition, to be the maximum of the stability number of the bags. Right? So again, stability number is the size of the biggest set with no edge inside. And they look at all bags. They look at the worst bag from the point of view of how big its stability number is. And then tree independence number of a graph, tree alpha of a graph, is the minimum over all 3D compositions of the stability number of the 3D composition. And if you have a graph with bounded tree alpha, you can solve max independent, max weight stable set or max weight independent set on its polynomial table. Okay. So let me just briefly mention some other variants of ways to describe the complexity of 3D composition, because this is kind of a growing field now, and we don't know much yet, but people think about all kinds of things. So for example, you can, so far we had bags of bounded size, bags of bounded stability number. You can think of bags of bounded diameter. And that's related to quasi-isometry, when two graphs have roughly the same distance function. It's related to an emerging field in graph, actually, it's an emerging field in graph theory called coarse graph theory, but coarse geometry, I think, a field that has emerged. So coarse geometry. Then there's bags of bounded domination number. That's also related to coarse graph theory. Bags of bounded matching size. That apparently has interesting algorithmic properties. So there are all kinds of measures that you can use. Really, you can take any graph parameter and define the width of your decomposition based on that graph parameter. Look at the worst bag with respect to that parameter, and now look at the best 3D composition, minimizing the worst bag. Okay, so that's a little advertisement for 3D compositions and different ways to measure their complexity. And now, so somehow by now we should agree that having small treewidths is good. Right, for now I'm going back to the classical notion of just measuring the size, but really everything I say, you can think of it in more general context. Okay, so which graphs have small treewidths? Now, of course, that's a question that doesn't make sense for one graph, right? Every graph has small treewidths. It has the treewidths of that graph. But the correct question is, or the good question is, for which graph classes C does there exist a number so that for every graph in the class, the treewidth is at most that number, right? And then we'll say this graph has bounded treewidths. And like I said before, what's small? So definitely, if it's a number, if it's 100 or 1,000, that's small, but maybe growing slowly with the number of vertices should still count as small. And then you can argue how slowly is slowly, discuss how slowly is slowly. So that's kind of the general framework. Now I want to make it even a little bit more concrete, because to ask for which graph classes is too broad, right? For which graph classes? For graph classes that have this property. So that's not the right question yet. So instead, let me say for which families, so I want to make this kind of a more precise question. I'll say for which family's H does there exist a constant or a function so that every H-free graph G has treewidths at most C of H, or has treewidths at most that function of its number of vertices. So I'm not just going to ask for which classes, I'm going to ask how to describe these classes by forbidden structures. Right? And that's kind of where structural graph theory comes in. You describe something by forbidden structures, and then you you try to understand classes in which the structures are forbidden. Okay, so that's good. That's almost a question that one can start thinking about, except what's a containment relation, right? If I say H free, then I need to say free in what sense? And it turns out the situation is different for different containment relations. So let me talk about that now. So first of all, there's this kind of simplest containment relation in graphs, and that's the subgraph containment. It's, H is a subgraph of G if H can be obtained from G by deleting vertices and deleting edges. And that's something that was answered in almost 40 years ago in 1986 by Robertson and Seymour. They said, I did that again. They said, okay, what's happening? They said that a graph G, in order they said for every T there is a C, so that if a graph G does not contain a subdivided wall as a subgraph, then the treewidth of G is at most C. Let me tell you what a subdivided wall is. So this is a wall. Let me not define it precisely, but it's built from bricks. It's a cubic graph built from bricks, or subcubic graph built from bricks. And a subdivided wall is when you take this and you take a subdivision, right? Put vertices of degree 2, as many as you like in every edge. So subdivided walls is an infinite family of graphs, right? So you fix T, that's one graph. Now you look at all subdivisions, that makes it an infinite family. And they proved if for every T, if you exclude this infinite family from G, then the treewidth of G is at most. Okay, and then there's a way to say this in terms of minors, which maybe is not as important right now, but it's exactly the same statement. For every T, there is C, so if G has no T by T wall as a minor, then the treewidth of G is at most. Okay, so for subgraphs and for minors, we know the answer completely. It's this theorem that tells you when treewidth is bounded. So now I want to move on to another graph containment, and that's something called induced subgraphs. And what's an induced subgraph? I'm not going to talk about induced minors, but I will talk about induced subgraphs. So what's an induced subgraph? Well, it's like a subgraph in the sense that you're still allowed to delete vertices, but what you're not allowed to do is just delete edges. So H is an induced subgraph of G if the vertex set of H is a subset of the vertex set of G, and two vertices are adjacent in H if and only if they were adjacent in G. Right, so if I kept two vertices and they were adjacent, I'm not allowed to remove the edge between them. Okay, so let's do an example. This is G. This is an induced subgraph of G because to get this from that, what you do is delete this vertex and keep all the edges. This is not an induced subgraph of that, because to get this from that, you would need to keep all the vertices, but somehow get rid of this edge and that edge, and that's not an allowed operation, okay? And I'll say family of graphs is hereditary if it's closed under taking induced subgraphs. I'll also use this notation to say that H is an induced subgraph of G. So, okay, so now I want to think about this question, but when the containment relation is that of induced subgraphs. And that's something new that started about 10 years ago. So let me show you some examples of graphs with large treewidths, right? If I want a characterizations of families with small treewidths, the right place to start is to look at families with big treewidths. So here they are. Big cliques have big treewidths. In fact, remember that trivial 3D composition I started with, where you put all the vertices in one bag? That's the only 3D composition that this graph admits. So the treewidth is n-1. Big complete vector graphs have large treewidths. They have K and N has treewidth N. Subdivided walls, we already said, have large treewidths. And then there's another thing that, if you think about it for a short while, you come up with, that's something called the line graph of a subdivided wall. So let me not tell you what a line graph is if you don't know, but what you would do here, every vertex of degree 3, right? So here, every vertex of degree 3 is kind of a closed junction, replace it by a triangle junction. And that's in this case, you'll get the line graph. So it turns out this graph and this graph have the same treewidth, okay, close treewidths. So this is another example of graphs with large treewidths. But the thing is, remember the Robertson-Seymour theorem for subgraphs? They said it's enough to exclude subdivisions of walls. For induced subgraphs, it doesn't work like that, because for subgraphs, if I exclude a large subdivision of a large wall, that forbids all big complete graphs, that forbids all big complete vector graphs, that forbids all of those, right? Because it's a subgraph of them. But for induced subgraphs, all these examples are independent. A big complete graph does not have any induced subgraphs other than other complete graphs. So this is a new family, not contained in big complete graphs. This is a new family. This is a new family. Those are not induced subgraphs of this because those have vertices with 3 pairwise non-adjacent neighbors, and these don't. Those are not induced subgraphs of this because those have triangles and these don't. So it's all independent. And to make things worse, let me show you another example. It's an example that was found by James Davis and independently by Postman and Pohata. Actually, I should say it in the opposite order because Pohata was 10 years earlier than Davis, but then somehow it got lost. So here's the example. You take many paths and you take many vertices, each with a neighbor in each path. And this is another graph. It doesn't contain anything I've shown you so far as an induced subgraph. And conversely, it's not an induced subgraph of anything I've shown you so far. And yet that's another example with big treewidths. Now, all these graphs, they have really, really big treewidths. They have treewidths polynomial in the number of vertices. In fact, the first 2 bullets, it's linear in the number of vertices. Then the walls and their line graphs, that's square root of the number of vertices. And this guy, it's also square root of the number of vertices. So really, remember we talked about maybe not asking to bound treewidths by number, but to bound it by a slow growing function of the number of vertices. So this is not even in that realm. Okay, so let's go further. Here are some examples where treewidth is still not bounded, but at least it's logarithmic in the number of vertices. So this is one example. It's called the Death Star. You start with a path, and you take the red vertex, you take one vertex that has a neighbor, and you give it one neighbor in the path. And that breaks the path into 2 intervals, the left one and the right one. And now you take another vertex, and you give it a neighbor in each interval. And that breaks the path into 4 intervals. And now you take another vertex and give it a neighbor in each interval, and that breaks the path into 8 intervals. Keep going like that. And the treewidth of this is how many of these vertical vertices you've added. But every time you add a vertical vertex, you double the length of the path. So the treewidth is logarithmic in the number of vertices. And there's some other examples that may not explain them, but there are now many different families with this property. Okay, so that's another bunch of families with unbounded treewidths. So let me say a graph is T-clean if it does not contain big cliques, big complete vector graphs, big subdivided walls, and line graphs of big subdivided walls as induced subgraphs. And so these are the first obstructions to bounded treewidths that were discovered in the world of induced subgraphs. And the way this question, this whole area was born, people said, what else do you need to exclude in order to get bounded treewidths? And Korhonen gave a beautiful partial answer to this question in 2022. He studied graphs where the degree is bounded. So if you exclude all of those, your graph is T-clean. But in addition, you promise that the treewidth is bounded. And then, that the degree is bounded. And so he proved that every T-clean graph of max degree at most delta has treewidth that's bounded as a function of T and delta. And so that's very nice. And it's a lovely, lovely proof. It's like a 5-page proof. It's a beautiful result. But, so now we have to think about graphs with unbounded treewidths. So then with different collaborators, I started working on this. Essentially, I should not rewrite history. We were working on this even before Korhonin's theorem. We were trying to prove Korhonin's theorem, but he proved it. So we had some partial results before him. But then we continued with unbounded degree. So this is a theorem with my former student Tara Abrishami, Bogdan Aleko, and with Seper Hajibe and Sophie Spurkel. So we said, what if your graph is T-clean, plus you exclude one more graph? What kinds of one more graph would guarantee bounded treewidths? And turns out there's a nice answer to this. The only graphs that work are graphs that look like this. Every component is a subdivided star. And every graph that looks like this works. So it exists a C, which is a function of H and T, so that every H-free T-clean graph has treewidths at most that, if and only if H looks like this. So that was something we're pleased with. So then we went on, we said, what if you exclude a finite family of graphs? Right, so T-clean plus a finite family. And again, we have an answer to that. It's a little hard to describe it, but basically the answer is whatever finite family forbids this, something slightly more general than this, but basically this, any finite family like that works, and no other finite family works. So the question becomes, describe finite families that forbid this. Okay, so that was an answer. And then, so then we changed our perspective a little bit. Before there was treewidths, there was something called passwidths. Well, in parallel to treewidths, there's something called passwidths. So what's passwidths? It's when you, right? So treewidths is some representation of your graph by a tree. Passwidths is when you do the same thing, but the only trees you're allowed to use are paths, right? So you build your graph by taking small subgraphs and chaining them together in this kind of linear way. And that's also an interesting construction to look at, and it was understood for subgraphs before treewidth was understood. Robertson and Seymour in 1983 showed that passwidth is bounded if and only if you forbid subdivisions of a binary tree as a subgraph. So what's a binary tree? Well, this is a binary tree of height 4. And you can understand what's a binary tree of height 5, right? Add some more, add 2 more leaves at each of this. So to me, there are different ways to kind of denote binary trees, but let me say BT is a binary tree of height T. So they prove for every T is a C, so that if you don't have a subdivision of BT as a subgraph, then passwidth is bound. And then we have a similar result for induced subgraphs. So it's a theorem of Seper, Hajibe, and Sophie Spurkel. For every T there's C, so if G does not contain, I'll tell you in a minute what, as an induced subgraph, then passwidth is bounded. So what do you need to exclude? Well, you have to exclude big cliques and big complete backpack graphs, right? We already know that treewidth is huge, so certainly the passwidth is huge. You need to exclude subdivided binary trees. Now, just like with walls, we had walls and we had their line graphs. It's the same deal with binary trees. We need to exclude subdivided binary trees and their line graphs. Yeah. So you exclude the subdivided binary trees of height T, you exclude their line graphs, you exclude big complete graphs, big complete backpack graphs, and then you need to exclude something that we call T-generalized T-stars and T-generalized David Pohata, which is a generalization of this graph and a generalization of that graph. And again, I will not explain exactly how you generalize them, but it's something that started there. And then if you exclude all those things as induced subgraphs, you get it to pass with this boundary. And it's an if and only if theorem. So it's a very nice answer to a natural question. Okay, so that's passwords. So then, but for treewidth, it's somehow much harder. We've been working on it for years and still couldn't finish it for treewidth. But then just last year, came a theorem of Aleco, Bonnet, Rognon, and Villafana, and they proved that you're not going to get a nice answer to the treewidth question. You're not going to get a hereditary family of abstractions, except it's a family of all graphs, right? If I want to say, here's a family so that every graph of large treewidths contains a member of this family as an induced subgraph and with large treewidths, right? So that it's necessary and sufficient. Then the only family that would work is a family of all graphs. So you're not going to get a nice answer like that if you replace treewidths with passwords. Okay. But on the other hand, by now we became convinced that bounded treewidth is not the only interesting situation. We should also think about logarithmic and polylogarithmic treewidths. And for that, there's a nice conjecture. The conjecture says, if you exclude a big clique and you exclude, so I wrote here induced minors, but I can say it also in terms of induced subgraphs. I don't know exactly what the induced minor is, but it's just like, so what subgraphs are to minors is what induced subgraphs are to induced minors. Some other containment relation that's related to induced minors, to induced subgraphs. So if you exclude big walls as induced minors and you exclude big complete backtied graphs as induced minors, then the treewidth is polylogarithmic in the number of vertices. Let me maybe say this in terms of induced subgraphs, make it a little simpler. So you would need to exclude subdivided walls. You would need to exclude their line graphs. And then you would need to exclude the same generalization of this we had to exclude for passwords, and the same generalization of that we would need to exclude for passwords. So there's a complete induced subgraph version of this conjecture, which I just didn't write down. So if you exclude all of that, then treewidth is polylogarithmic in the number of vertices. And that's a nice question. That's a question that might have a good answer. And by the way, there's also a similar conjecture for tree independence. Right? Remember tree independence number, where you look at the biggest stable set in a bed instead of the biggest size of the bed. And the main difference between tree alpha and treewidth is that for treewidth, cliques are your enemy. Cliques have large treewidths. But for tree alpha, cliques are your friends. Cliques have tree alpha 1. So somehow that's where the difference is. Okay, so anyway, so we worked on these questions of polylogarithmic treewidth and had all kinds of results throughout the years. Every theta triangle free graph has logarithmic treewidths. Every even whole free graph has logarithmic treewidths. Let me maybe not tell you exactly what all this means, but these are all natural concepts in the theory of induced subgraphs. These are all graph classes that have been studied structurally from the point of view of induced subgraphs, and now we got logarithmic bounds on their treewidths. And then skip that. More examples. If you exclude tetas and pyramids and the line graphs of a subdivided wall, and you exclude some tree and a theta in the line graph of a subdivided wall. In any case, these are all some examples of natural graph classes from the point of view of induced subgraphs, and you can prove that they all have logarithmic or polylogarithmic treewidths. And now let me talk about tree independence analogs. So it turns out that all these theorems have tree independence analogs. Now, for treewidth, we're able to get a logarithmic bound. For tree alpha, the bounds are polylogarithmic. And we don't know what the truth is. We don't know if the truth is, like, for example, here, for treewidth, it's log the number of vertices. For tree alpha, it's the square of the log number of vertices. So we don't know what the truth is. And I would like to know. Similarly for even whole free graphs, similarly for all kinds of other things. And that tells you that, again, you can solve various algorithmic problems in quasi-polynomial time. Now, again, the advantage of thinking about tree alpha instead of tree width is that you don't need to exclude big clicks, right? When you get that tree width is logarithmic with a big click excluded, you get nice algorithms for graphs in that family that have bounded click number. When you don't bound, when you think about tree alpha, you're in the same algorithmic situation, but you didn't need to exclude clicks, so it's much better. Okay, so now, so there's some more results of tree alpha. Again, I'll not tell exactly what they say, but many graph classes where we could bound tree alpha by sometimes constant function, but usually a quasi-polynomial. And now, it's starting to seem that maybe it's not a coincidence. So first of all, one thing you can notice is that if your tree independence number is bounded, then tree width is bounded as a polynomial function of the click number. That's just Chudnovsky number, right? In every bag, the click number is most the click number of the graph. The stability number is tree alpha, and so the size of the bag is at most this. Okay, so then Dallard, Milanich, and Storgel made the conjecture that it's if and only if. If tree width is bounded as a function of the click number, then tree alpha is bounded. Except that's false. That's my theorem of Nicolas-Trottignon. We have a construction that has where tree alpha is bounded, but tree width grows. Sorry, other way. Where tree width is bounded as a function of the click number, but tree alpha is not. Okay, so just one thing I want to say. So that it's like this theorem says if tree alpha is bounded, then tree width is bounded by a polynomial function of the click number. So the conjecture that would make sense to make it if and only if tree width is bounded as a polynomial function of the click number, then tree alpha is bounded. Right? That's a real if and only if. You shouldn't expect that a much worse bound on tree width would still result in a constant bound on tree alpha. But that's also false. That's what it says here. My theorem of Trottignon shows that even if you start with a logarithm with a polynomial function, you still get you still don't get bounded tree alpha. Okay, so that's that didn't work, but turns out something very much like that works. So let me just show you this conjecture again. The conjecture is if tree width is bounded, excuse me, as a function of the click number, then tree alpha is bounded. So what if I relax my expectations and I say tree alpha is bounded, except I'm allowed some polylogarithm of the number of vertices, right? So it's not going to be bounded. It's going to be growing slowly as the number of vertices. If tree width is bounded as a function of the click number, then tree alpha is at most something times polylog of the number of vertices. Well, that turns out to be true. And if you look at what it says here, actually something stronger is true. Not only am I bounding tree width as a polynomial function of the click number, I'm allowing a logarithmic factor of the number of vertices, right? So the assumption is much weaker. Tree width is a polynomial function of the click number times something that grows slowly in the number of vertices. And still, tree alpha is bounded as a polynomial function of the number of vertices. So that explains many of, not all, but some of these results I showed you here. Always worse bounds. That theorem that I showed, the general theorem gives you much worse bounds. So to get good bounds, you still need to do more. But we have this explains some connection between tree width and tree alpha. And let me stop here. Thank you very much.